Okay, so last time we had talked about the quotient of line segments. So this was how we constructed that quotient of lengths. So B over A was constructed in this way using parallels. Um, so knowing this construction of the quotient of line segments, and I'm going to get into a little bit of the history as that is like how the Greeks thought of products and quotients of line segments. But knowing this essentially gives us kind of a nice list of things that we can construct doing this, but it's not completely exhaustive. So what do I mean by things here? So specifically, I'm talking about numbers that can be constructed. So the Greeks thought of this as being giving us like the full extent of numbers that can be constructed. And what I mean by that is if we start with unit length, so if I'm going to just draw segment here, some length, I'm going to say that that's unit length. So if this is O and this is U, and we call this unit length, okay, what does this mean? So the idea here is that through addition, I could take this one and add it to itself however many times I want to. And so if b is a natural number, or if b is a positive integer, right, so then if b is a positive integer, or natural number, I can obtain b from unit length by addition of line segments, right? So b is just the line segment 1 added to itself, b times, right? So this is the idea here, okay? And so I can construct any positive integer in this way by adding unit line segment to itself as many times as I need to. I mentioned this when I talked about how to construct this segment from what I had started with here for multiplication of line segments. But now that we have quotients, this allows us to construct numbers that are a little bit more general, right? So then, thus, if n and m are positive integers, I can construct n over m. I can construct the ratio, okay, using this construction of quotients of line segments. Okay. All right. Now, what is this saying? I.e., I can construct rational numbers okay, so but it is important to note that this is not exhaustive. Okay, so it doesn't end with rational numbers, as we'll see here in a few minutes. So this isn't the end. Okay, not by a long shot. So, and in fact, this puzzled the Greeks a lot, because for the Greeks this was the end. Rational numbers, that was just numbers. In fact, if a number wasn't rational, the Greeks didn't consider it a number. Okay, but we'll see why that's a little bit confusing because you can very much construct numbers, or you could very much construct lengths using just compass and straight edge that are not rational, that are irrational. And so the set of all constructible numbers, that is, numbers that could be constructed in this way using compass and straight edge, are not the same as the rational numbers. Okay, there's more of those. There's more constructible numbers. Okay, so, but this is not everything that can be constructed. But this is not the full list of constructible numbers. Okay, as we'll see, there's a very, very simple construction that shows that this isn't the case. Okay, so that's an important bit there that shows kind of what the Greeks were thinking in terms of how they were constructing these numbers. So anyway, what is next? I had so we had previously discussed the Thales Theorem, but we didn't prove it. So we won't prove it until a little bit later. Like a couple more lectures, I'll prove it. So we previously discussed the Thales Theorem. And it turns out that the Thales Theorem is a more general fact that is related to a discussion of similar triangles. So if you recall, what are similar triangles? So recall a definition. So two triangles, say ABC and A prime, B prime, C prime, are called similar. Okay, if their corresponding angles are equal. Okay, i.e., if angle at A is equal to angle at A prime and angle at B is equal to angle at B prime and angle at C is equal to angle at C prime. Now, once we've written all these things, we can say, for the sake of the diagram that's coming up, we'll call the angle at A and A prime alpha, the angle at B and B prime beta, and the angle at C and C prime gamma. Okay. Now, this is the definition of similar triangles. The reason this is the definition of similar triangles is that it is enough to give us exactly what we care about. But the actual thing that we care about for similar triangles is not that their corresponding angles are equal. What we actually care about is that it entirely describes the notion of triangles that are similar in scale. Okay, that's what the word similar means. What does that mean? It means that corresponding sides are proportional. Okay, but the most important fact about similar triangles is that corresponding side lengths are proportional. So, what does that mean? It means that if you have two similar triangles, then these two similar triangles are scaled versions of one another. So I'll use the term scale even if I mean a shrinking. So I won't say scale, or I won't say dilation or like shrinking, I will say just scale. So even if something has been scaled by 1/2, that's still scaled. So the corresponding side lengths are proportional, meaning that when you have two similar triangles, they are similar in shape. Okay, means that the shape of the triangles is the same. Okay, but one or both of them have been just scaled from the other by some scale factor. Okay, and that scale factor is constant among the sides. All right, so we'll talk about that in a second. Quick, easy example is imagine an equilateral triangle, right? You already know from your previous geometry experience that an equilateral triangle has angle measurement 60, 60, 60, right? If you're thinking of degrees, right? Or you know that it's an equilateral triangle, so all the angles have to be equal. So if they all sum to pi, then each of them is pi over 3. Okay, so what this means is any equilateral triangle you draw has to have those same angle measurements. So obviously any equilateral triangle is similar to any other equilateral triangle by this definition. Okay, but think about what that means, right? So you can think of unit equilateral triangle, so equilateral triangle with side length 1, 1, 1. If you think of unit or equilateral triangle with side measurements 3, 3, 3, right? Well, those side lengths are in fact proportional, right? They've been scaled by 3, and so you've just taken your original equilateral triangle and you've blown it up by a factor of 3, right? So that is essentially what's going on with every similar triangle here. So corresponding side lengths are proportional, and this is the key defining property that we care about for similar triangles. Okay, so I want to prove this fact: corresponding side lengths are proportional. Okay, so let's prove this fact. So proof of similar triangles have proportional corresponding sides. Okay. Okay. All right. So, how does this go? The idea, first of all, is say that I have two triangles, ABC and A prime, B prime, C prime, that are symmetric. So, suppose triangles ABC and A prime, B prime, C prime are similar. Okay. Now, without loss of generality, we can assume that one of these is the bigger triangle. So let's say that this one is the bigger one. Okay, so A prime, B prime, C prime is the bigger one. Okay, and in fact, let's say that this bigger triangle showing up in this diagram that I've drawn is A prime, B prime, C prime. Okay. Now, since these are similar, since A and A prime, or I should say, since the angles at A and A prime are equal, I can move triangle ABC until I get the picture to the left. So until I get this picture here. So what picture is that? Well, I can line up the points A prime and A, and I can put that triangle ABC inside the triangle A prime, B prime, C prime like this. Now, how do I know that I can do that? Okay, so the way that I know that I can do this is these angles are equal. And what it means if they're equal, it means that if I do this operation of what I'm doing here really is applying an isometry to this triangle. So I'm applying a transformation to this triangle, ABC, that is not changing any of those properties that I care about. It's only changing location. Okay, now I don't have coordinates here to describe that exactly. So I'm just thinking, completely abstractly moving this triangle around, or rotating this triangle if I need to, or reflecting this triangle if I need to. None of those operations or combinations of those operations affect the angle measurements or the lengths. Okay, and so I don't have to worry about altering anything like that. So I can slide this in until this is the picture that results. And so we called this angle at A prime and A alpha. We called the angles at B and B prime both beta. We called the angles at C and C prime both gamma. Okay. All right. So then, if I call the length from A to C B, and I call the length from A to B C, okay, then correspondingly the length from A prime to B prime would be C prime. So then this little piece would be C prime minus C. Similarly, if this side, so why am I, you might think that it's weird to call this side C prime or this side C. The convention typically is that in a triangle, we view the angles as determining the sides, right? So for higher polygons, that doesn't work. But for triangles, it does. So you associate the side length opposite the angle C with C. That's where the convention comes from. Of course, you don't have to do it that way, but that's typically what's done. So same thing here. This length is B prime. So then this piece is B prime minus B. Okay. Okay. Now, what does this tell us? Okay, note, since BC and B prime, C prime both meet, say, AB prime. We could have used this as well. Both meet A B prime at angle beta. They are parallel. Okay. So these two lines are parallel. Of course, sometimes you see this thrown in as a symbol to say that those things are parallel. Okay. All right. Now, what do I need that? I need that for Thales theorem, right? So by Thales theorem, right, we know that Thales theorem says something about proportional quantities and triangles that are set up with this parallel configuration in this way. So by Thales theorem, this says that B over C is the same thing as B prime minus B over C prime minus C. So B over C is equal to B prime minus B over C prime minus C. Now this isn't quite what I want here, okay? What I want is that B over C is the same thing as B prime, this whole length, over C prime, this entire length. Okay, that's what I want. Okay. All right. So they have proportional sides. I really don't need the word corresponding here. That's for a particular statement that I want to say. So I got rid of this corresponding. I don't really need that. Okay. So to say that they have proportional sides, I need this right-hand side fraction to be B prime over C prime. Okay, so what if I I clear denominators, right? So clearing denominators. So multiplying both sides by c times c prime minus c. So clearing denominators yields, so I'm multiplying both sides by c times c prime minus c. So I get b times c prime minus c is equal to b prime minus b times c, i.e. I get b c prime minus bc is equal to b prime c minus bc. So I have the same quantity minus bc on both sides. So I can add bc to both sides and those go away, and what I get is bc prime is equal to b prime c. Aha. Okay. So then dividing by c prime, I get b over c is equal to b prime over c prime, which is exactly the statement that I want. Okay. So the corresponding sides opposite to angles beta and gamma are proportional. Okay. All right. So I only showed this for two sides, but I could have actually done this in any pair, right? I could have matched up any other angle here. Note, I could have matched up either of the other two angles. To get similar, no pun intended, results. Thus, I'm done. So why am I done? Just really quickly. So I'm done because I could have this triangle, the way that I drew it here, I could have done it in such a way that I matched up the angles at b and b prime instead. Okay, if I had done that, I would have gotten a situation similar to how I drew Thales Theorem originally. So my parallel lines would have been this one and the bottom piece, and I would have gotten similar proportions matched up for two other sides. And then similarly, I could have matched the angle down here instead and gotten a different pair of proportions there. So that's the idea. And any of those would have worked. The exact same logic would have worked here. And thus, this is what we get now. Why is this important? The reason this is important, and the reason why similar triangles have a special name, is specifically that they are important for their applications, not just practically, but also in the rest of geometry. But practically speaking, things like, house plans, blueprints, why is any of that stuff useful? Because if the angles are kept the same, then essentially, if you're careful about how the angles are done in the thing that you're drawing, then essentially you can have a complete to scale drawing of whatever region you want to describe that fits on a single sheet of paper and accurately, in terms of the shape, describes what it is that you're looking at, right? So this gives you a way of scaling down potentially gigantic plans onto a very small sheet of paper in a way that's accurate. If you have ever seen shapes like the Nazca lines, or even human-made crop circles, right? So any sort of geometric shape that you've seen produced on a huge scale, right? So think, if you don't know what the Nazca lines are, you can look those up, or any of those geometric shapes. What they are giant geometric and like pictures of, say, lizards and spiders and things like that were drawn by by people thousands of years ago. And the way that those drawings are produced is you have in mind the drawing that you want, like on a small scale. And then if you keep your angles the same, all the turnings that you do, then all you need to do essentially is worry about the angles in question. And if you're careful, you can blow up or scale that picture to any size you want. So you draw a small image of spider on paper. If you pay attention to the angles used, and you're careful in marking this off, you could turn that, picture of spider into a gigantic image that spans like miles and miles across. So that's one practical application. But we're going to see plenty of applications of this stuff coming up. Okay. So here's one immediate application. So returning to this question of constructible numbers, here's a fact that the Greeks found, well, some of the Greeks found very unfortunate, which is that the diagonal of unit square is square root of 2. This is a symbol we're using here, so I'll talk about that in a second. So the diagonal of unit square is square root of 2. Okay, so let's draw unit square here. I'm going to call it unit square, even though, as you can see by me marking off with this straight edge here, I'm cheating. Wait, what? I must have not paid attention and literally, there, ignore this part. Don't know what I was doing there. Okay, so the diagonal of unit square is length square root of 2. So let me draw in the 4 triangles that split unit square in this way. So here's side length 1. Okay. So I'm going to look at a single length of this diagonal. Say, call the length of one of the diagonals D. Okay. And so the length of this entire thing is D. Now, I took a shortcut here and just quickly sketched this using my straight edge, but if I were constructing this using just compass and straight edge, what would I do here? Well, you know how to construct a square. Okay, so you know how to construct a square using compass and straight edge. Here you are bisecting these corner angles of this square. Okay, so you're bisecting the corner angles of the square. And so what you are doing here, because you're bisecting these corner angles, you're splitting this into 4 isosceles triangles, or forget about that for a second. You're splitting them into 4 triangles that have a right angle and then 2 half right angles, right? So you have 1 right angle and 2 half right angles, and that's true for each of these triangles. So these are 4 similar triangles. Okay, so below we have 4 similar triangles. Okay, so we have 4 similar triangles. I mean, technically there's more triangles here than these four, but I'm specifically talking about these tiniest four. But technically there's more, right? There's this triangle, for instance, tracing over. And there's this one. There's more, right? This is like one of those trick questions where you're asked to count how many triangles show up in some figure, right? Okay. So if the length of an entire diagonal is d, so that's d, what about these half diagonals? Well, they're d over 2, clearly, right? So here's d over 2, and here's d over 2, and here's d over 2, and here's d over 2. Okay. All right, but all these side lengths are 1. Okay. Now, these four smaller triangles are all similar. Also, but wait, there are more similar triangles. Well, in fact, these triangles that are half of unit square are similar to each of the smaller triangles. Right? So not only are each of the four smaller triangles similar to each other, because each of them has right angle and two half right angles, so they have the same corresponding angles, which means by that theorem we just proved, they have proportional sides. But also, these half square triangles are similar to each of the smaller triangles. Okay, thus, by the fact about similar triangles we just proved, if I look at any of these similar triangles and consider short over long, okay, what is short over long in my bigger triangle? So keep highlighting this one. In this one, what is the short side and what is the long side? Well, the the short side, of course, we know these are isosceles triangles, so there's more than one short side. There are two short sides because they're the same length. But in this bigger triangle, my short side has length 1. Right? Because this diagonal part in that triangle is longer. How do I know it's longer? It is opposite the larger angle. Okay. It's opposite the longer angle, the larger angle. So I don't need to know too much coming from, what I'm assuming, and I'll be more careful about that in the next chapter. But this is opposite the larger angle. Also, this is something we'll talk about later, is the triangle inequality, that this is a shorter distance than these two things sum together, but is longer than, of course, either of those shorter sides. So anyway, short in the bigger triangle, the short side is 1. Divided by long, well, the long side in the bigger triangle is length d. But since this triangle that I've highlighted has to be similar to each of these four triangles, in each of these four triangles, what's the short side? Right. So what is the short side in these smaller triangles? Well, the short side in these smaller triangles is d over 2. Right? And the long side is 1. And so 1 over d is equal to d over 2. Right? i.e., 1 over d is equal to d over 2, which means that d squared is equal to 2. Now, this means that d is equal to square root of 2. 1, we take the positive root because it's a length, but really here, I didn't take a square root. This is purely a symbol. So I used the symbol radical over 2 to denote this. This is actually the meaning. Okay, so when I say d is equal to the square root of 2, what I really mean is d is a number such that d squared is equal to 2. That is, d times d is equal to 2. That's what's meant by this. Okay, now, why is this interesting? All right, so the Pythagoreans, so as the Pythagoreans supposedly figured out, as the Pythagoreans noted, square root of 2 is irrational, i.e., it cannot be expressed as a ratio n over m, where n and m are positive integers. Okay. So the story goes that the Pythagoreans were all on a ship when one of them discovered this, and they were so upset that the person who discovered it was thrown overboard. Now, whether or not that's true, I don't know, but it's funnier to think of it that way. So let's prove that the Pythagoreans were right. So the square root of 2 is irrational. You've probably gotten sick of this proof by now, but if not, or if you have managed somehow to navigate through your math career without having seen this proof in its entirety, I think it's worth at least going for. So suppose that, or suppose not, i.e., this is a proof by contradiction, so suppose that square root of 2 is equal to n over m for positive integers n and m with n over m in lowest terms. Okay, so they share no non-trivial factors. Right, I can't reduce n over m any further. Okay, well, square root of 2 being equal to n over m, what does this mean? This means if I square both sides, 2 is equal to n squared over m squared. That's just how this algebra works, which of course means that 2m squared is equal to n squared. What this says is that n squared is even. Okay, so n squared is even. N squared is even because I've written it as 2 times something. Okay, and 2 times something is always even. Okay, right, because m is a positive integer. So this is 2 times a positive integer. Okay, but this, if n squared is even, then n has to be even. i.e., n is equal to 2k for some integer, for some positive integer k. But then, if n is even and is equal to 2k, then 2m squared is equal to 2k squared, which is equal to 4 times k squared. Simplifying this means that m squared is equal to 2k squared, i.e., m squared is even. But using the same logic, if m squared is even, then m is even. And I can stop there. Why? If n is even and m is even, then n and m have a common factor of 2 at least. This is a contradiction. This is a contradiction. And the reason why this is a contradiction is I assumed that these were in lowest terms. So I assumed they were in lowest terms, but it turns out they both have a factor of 2 in common. So intuitively, what this would lead to is a fraction that never reduces, right? You can always just keep dividing by 2, because once you get to this part, you reduce it, and then you can repeat the exact same process over and over again. So that doesn't make any sense. Okay, so they have a common factor of 2. This is a contradiction, so this is no good, i.e. square root of 2 cannot be written as n over m for n and m positive integers. So it is irrational. That is not rational. Okay. So what is the point of saying this or going through this? The point of going through this is to show that even in something extremely seemingly innocuous here, namely it's just the diagonal of unit square. In the diagonal of unit square, you can see exactly that there's an irrational length showing up, right? So there's an irrational length showing up in the diagonal of unit square, and so in kind of one of the most simple things showing up in geometry that we've constructed in this way, you get an irrational length. So you can very much construct this irrational length. It's just the diagonal of unit square. Okay, so that should tell you that, you know, there's more than just the rational numbers in terms of what can be constructed. Okay, so returning back to this question of what can be constructed. So brief discussion on what can be constructed. Of course, when we say constructible, we mean by compass and straight edge. So, quickly going to move, and it won't seem totally obvious why I'm talking about these things right now, but here you see I have a depiction of what are called the 5 platonic solids, or the 5 regular polyhedra. Okay, so regular polyhedra are the analogous objects to regular polygons in the plane. So these are 3-dimensional objects. The idea is that they have faces. The faces are all regular polygons, okay, and these have to close up, okay. And it turns out that if you specify that you want to talk about regular polyhedra, that only 5 of them exist. Okay, so you might recognize these as if you're an avid Dungeons and Dragons player, you might recognize this as D4, a D6, a D8, a D12, and a D20. Right here. Hold on, we got icosahedrons lying around here because that's how cool we are. Let's see. Here's a nice, let me just grab a nice icosahedron real quick. So there, is a nice icosahedron. You can see it goes all the way up to 20, right? So here's my icosahedron, but you notice that my icosahedron, which is it's the most complicated of the Platonic solids, it has 20 faces, it has 20 sides. The octahedron has 8 sides, dodecahedron has 12 sides, cube has 6 sides, tetrahedron has 4 sides. So this one's the most complicated, but it's actually built out of equilateral triangles. So if you see really closely, there's each equilateral triangle face. So the tetrahedron, the octahedron, the icosahedron are all built from equilateral triangles. The cube is built from squares. So already in this course, first thing we did was construct equilateral triangles. The cube relies on squares, and we've constructed a square. So we could actually construct everything required for these. The only thing that is different is the dodecahedron requires construction of regular pentagons, regular 5-gons, which we haven't done yet and is a little harder than these two. Okay, but we'll do that in chapter 2. So we'll do that soon. The one thing I'll say about so the one thing I'll say about this is it might be confusing at first, like why this is all. There's no other possible Platonic solids or equilateral triangles, or sorry, regular polyhedra. If you think about what has to occur at each vertex, like how these things have to come together for this figure to close up, you'll see that there's just a very easy limit that happens where eventually you either reach an object that's flat, so it never closes up, or it's bent in a weird way that it wouldn't close up. So basically, you have some inherent restrictions on how these things can meet at angles, and that's why you only get these options. So the reason I wanted to mention that is that you might say, wow, so all I needed to construct those were equilateral triangles, squares, and pentagons. It turns out that those were the only shapes actually constructed in antiquity. Any of the other polygons, other than sides 3, 4, or 5, weren't constructed until thousands of years later. And the reason why is it can be really tricky, and also it gets entangled with some stuff that's not quite geometry, it's more number theory. So in that vein, I had mentioned previously, so here's an interesting fact. Okay. The answer to the question, which regular n-gons can be constructed, relies on Fermat primes. What are Fermat primes? I mentioned these before. So, a Fermat prime looks like the following. So, f sub n we'll call 2 to the 2n plus 1. If this is prime, it is called a Fermat prime. Okay, so if this number 2 to the 2n plus 1 is prime, it's a Fermat prime. Now, where do we come up with this? If you just wrote this as 2 to the m plus 1, it turns out that the only time that can possibly be prime is when that m is a power of 2. So that's why it takes this funky form that it does. This is something that is required. When you have 2 to a power plus 1, the only time that is prime is when that power is a power of 2. Okay, and so when this is prime, it's called a Fermat prime. So the question is, when is it prime? The reason it's called a Fermat prime is it's named after Fermat, same guy who came up with Fermat's little theorem or Fermat's last theorem, any of those theorems named after Fermat you might have heard of. So the reason it's called a Fairmont prime is he believed all of them were prime, but it turns out that f sub 5 is not prime. So f sub 1 is 2, or sorry, f sub 0, since we can define that, is 2 to the first plus 1, that's 3, so that's prime. I'm not going to write prime, I'm just going to write checks here. F sub 1 is 2 to the 2 plus 1, that's 5, that's also prime. F sub 2 here is 2 to the 2 squared, so that's 2 to the 4 plus 1, so that is 17, that's also prime. F sub 3 is 2 to the 8 plus 1, so that is 256 plus 1, so 257. It turns out 257 is also prime. And f sub 4 is 2 to the 16 plus 1, which is, this is 65,536 plus 1, so 65,537. 65,537, which it turns out is also prime. Okay, but f sub 5 is, how does this factors? F sub 5 is 641 times 6,700,417, i.e. is not prime. Now, it is unknown how many of these, or if there's another prime. It is believed that none of them are prime after f sub 4. So it is currently unknown if any more are prime. So Fermat believed all of them were prime, but f sub 5 is not prime. They've only been factored fully up to f sub 11, I think. After that, they're known to be not prime. A lot of them are known to be not prime, but none of them have been factored, I don't think, because they're pretty huge. This is an exponential thing, so it's getting pretty big. So anyway, these are all known to be prime, though. So why am I going through all this? What does any of this mean? This is very much related to which regular n-gons can be constructed. So it's related to it in the following way. So let me quickly, I'm over time, but this is fun stuff, so I can't stop. So here is the fact. Okay, a regular, so let n be greater than or equal to 3. A regular n-gon can be constructed by compass and straight edge if and only if n is a power of 2 times a product of distinct Fermat primes. Okay. Now it can be, it could be an empty product. So you know that I can construct a regular 4-gon, for instance. So that's fine. I.e. n is equal to 2 to the a times f sub n minus 1 times f sub n minus 2, or sorry, n sub 1, n sub 2, all the way out to n sub r, with a greater than or equal to 0, r greater than or equal to 0. So it has to be of this form. So this tells you automatically which things can be constructed and which cannot. So this is a fact that actually tells us, I'm not going to prove this, okay, because it actually has little to do with specifically what we're going to be doing. So we can construct equilateral triangles, we can construct squares now, that's what I had you do on the last homework. We can also construct regular pentagons. We're going to do that in chapter 2. It's a little bit harder, but we can do that. I can combine constructing equilateral triangles and regular pentagons to get a regular 15gon. I can bisect angles to double the sides of any polygon I've constructed. So if I've constructed a regular 15gon, constructing a 30gon, 60gon, 120gon is easy using bisecting angles. So then what else can be done? Well, this tells me exactly what can be done. Now actually doing them is hard. So Gauss, when he was 19, Gauss constructed the 17gon, and this was like 1796. So way after this was being considered by the Greeks. Actually, Johann Hermes constructed the regular 65,537 gon in 1894. Took 10 years. So that is sitting, that construction is actually sitting in a desk, I believe, or in a box somewhere in Germany. Of course, you can construct. So the power of 2 here comes from bisecting. You can double this thing, but this type of thing intersects with number theory in like an unexpected way, because you wouldn't think that what would this have anything to do with Fermat primes, these numbers being prime? What does that have anything to do with anything? So it's interesting to delve into this, and maybe if we have time later I'll do that. But anyway, so that discussion finishes what I wanted to do in the first chapter of this book. So that's more or less everything that I wanted to do in the first chapter. So we'll start on chapter 2 on Monday. So I will see you all in lecture then.